Flack math! Give me some math and I'll give you some flack. Flack math!
The first step of factoring is always looking for a GCF. What does GCF stand for? All right, so greatest common factor. So finding GCF, which is the greatest common factor. Okay? So for example, we've done this in the past. We've got, what's the GCF of like, of two numbers, but, well, first of all, let's do this. Let's factor this. When I say factor, that means I want you to take that engine apart. Okay, take it apart as much as you can. What are you left with? What'd you get? Can you do it in your head? All right, what is it?
21 times 10, 23 times 7, 2 times 5.
All right, so 2 times 3 times 5 times 7. All right, let's see if I get that. 21 times 10, 3 times 7, 2 times 5. Nice. So this is just 2 times 3 times 5 times 7. Okay, good. Now, if I wanted to factor this, then what are the factors of this? Well, it's still 2 times 3 times 5 times 7. But in algebra, all the factors are already listed nicely for you. X, y squared, z cubed. Okay? So what was it? Remember we had 80. 80, what was that? That was like 2 to the 4th times 5 times a squared b cubed c. Okay? So those are all factored out. All the engine parts are on the garage floor. They're all for everybody to see. Okay? So, this is important, and I'll tell you why in a minute. But it's important to know the factors of what you're dealing with. Not quite into, but I'm not going to judge. All right. Okay, now Saxon puts this little statement here and says GCF of 2 or more factors is the product of all prime algebraic, remember algebraic means numerical and literal, algebraic factors common to every term. Sorry, 2 or more terms, not factors. I'm sorry if you wrote that. It doesn't matter, factors, terms, same thing, but in this case we're talking about terms. It's not the same thing, but the same rule applies to factors as it does to terms. Common to every term. Okay? And so this is each to the highest power it occurs. So this sentence can be a little misleading and confusing. But I'm going to explain it to you, and if it helps, great. If not, then you can just ignore it. Okay? So if I wanted to find GCF of these terms, 6x squared, y squared, m squared plus 3 xy cubed m squared plus 3 x cubed y squared. I want to know what all three of those terms have in common. Okay? So, I'm looking for all the prime algebraic factors, literal and numerical, common to every term, each to the highest power it occurs. So the highest it occurs in every single term, not the highest it occurs total, but in every term. Okay? So first of all, numerically, what is the GCF of 6, 3, and 3? What goes into 6, 3, and 3? 1 does, but there's a bigger one, 3. That's right. So it's kind of like, yeah, you just want to know what the biggest thing you can divide out of it is. Okay? Now, algebraically is so much simpler. Algebraically, you don't really have to do much math. You just have to look at which letters they have in common. So they all have X's and Y's in them, right? The last one doesn't have an M, so M's not going to be part of the greatest common factor, okay? But how many X's are in each term? Well, there's an XX there. There's 2 X's in this term. There's only 1 X there. And there's 3 X's in that term. So out of all 3 of those terms, what do they have in common? How many X's? They all have at least 1. That's right. Okay? So when you're looking for the greatest common factor of the literal factors, all you're doing is looking for the smallest exponent. And if you don't see an exponent, then it's just 1. Okay? So they have 1 X in common. What about Y's? How many Y's do they have in common? 2. This is Y squared, this is Y cubed, this is Y squared. So you're just looking for the smallest exponent. So Y squared. Then what about M's? How many M's do they have in common? Yeah, nothing. These 2, if we were just doing the greatest common factor of those 2, then we'd be set. But if you include that last term, you can't include an M. Okay, so the greatest common factor is this. Then you're done. Okay? So when you're just finding the greatest common factor, you're just looking to see what they all have in common. So numerically, it's kind of like when you were reducing fractions and you try to figure out, okay, what's the biggest thing I can take out of both the top and the bottom number? It works that way with this too. What's the biggest number I can divide out of all 3 of those terms? Well, 3. And then with the variables, you're just looking for the smallest exponent. Let's do 3 examples and we'll call it a day. Here's example 1. Find the greatest common factor. Here it comes. 8z to the 4th m squared p minus 12 z to the 3rd m to the 4th p squared. Find the GCF, find the greatest common factor of that. Okay, take a couple minutes and compare with someone next to you if you want. And then I want to hear your answers. All right, when this song's done, I'm gonna go in. So compare with someone if you already got it. Compare with someone next to you. There it is, it's done. Okay, so numerically, our two numbers out in front, our coefficients are 8 and 12. What'd you get, Cheyenne?
4z7 m to the fifth e to the fourth.
Okay, I got 4, but then your z's, you're not adding the exponents. You're just trying to find the smallest exponent of each of the z's. But if you were multiplying them together, yes, you'd have z to the 7th, m to the 6th, and p to the 3rd. That's right. All right, so you got 4. That's awesome. Now we're looking at the variables. So z to the 3rd, because your two exponents of z are 4 and 3, right? So you're looking for the smallest one. This is what they have in common. Okay, I like to think of it as I've got two brothers and they both own Walmarts. Okay, so I need to. I feel bad if I go to this brother's Walmart, but so if I go to this brother's Walmart, then I have to go to the other brother's Walmart and buy the same things to be fair, right? Because that's not fair to buy something from this brother's Walmart but not my other brother's Walmart. So, but here's the deal. I want to buy Z's, as many Z's as I can. I'm stocking up, just in case something happens, I want to stock up. So I'm going to Mr. K-Flack's Walmart, and he's got 4 Z's on the shelf. But my other brother's only got 3. So how many am I going to buy from this brother? 3. They both have at least 3, so I'm going to take 3. Okay? So I got Z to the 3rd. What about my M's? How many M's am I going to buy from each store? 2. I don't want to be fair. I don't want to be unfair and buy more from this guy. Even though this brother has more M's, I'm just buying 2. What about P's? Just 1 P. All right. Is that what you guys got? Yes.
But if you're buying up, but if they only have that much, you're buying them out of stock.
I know. Oh, I'm doing them a favor, so they have to restock eventually. But it's a good problem to have when you have to restock because you've sold out of stuff. It's a good problem. All right. 1 more or 2 more? Let's do 2 at a time. Here we go. Example 2. I want you to try to find the GCF of 4x squared y cubed z minus 8 y squared x z cubed. And then I want you to find the GCF of 16 x squared y p to the 3rd minus 4 x cubed y squared p plus 2 x squared y squared p to the 15th. All right, find the GCF of those 2 examples. You need to compare with someone next to you, you can do that.
Yes, thank you so much.
You guys need more time? Doing all right? Okay. Who's ready to give me a GCF for example 2? What'd you get for example 2? Eliana?
4xy to the second z.
All right, so I'm looking at the x's. The smallest exponent I see is nothing, so just an x. The smallest y I see is a y squared. Smallest z I see is just a z. Awesome, good job. All right, who else for example 3? What'd you get?
Okay. I got 2x to the second yp.
So y, just yp?
Just y.
Okay, so the smallest exponent of x is 2 because there's a 2, 3, and a 2. Smallest y exponent is just y squared, so just a y. P cubed, p, and p to the 15th. So the smallest p is just p to the first. Very good. All right, does this seem pretty doable? You guys good with this? You feel like you can find the greatest common factor? Awesome, good job.
Black math, give me some math and I'll give you some flack. Black math.